happened due to some current issue, electricity problem. Everything switched on, and the stream ended actually. So that was supposed to happen at 3:15. Oh, it has come now. I think we got the link now. We'll be able to do installation. Yes, it's done. Okay, fine, sure. Oh, thanks. Okay, sure, thanks.
Okay, welcome to this live session of the MOOC course on chemical process intensification. So we have given a lot of information on the chemical process intensification in several lectures. I think you have enjoyed the course, and if any problem with you that you are not understanding the course material, please uh, write to me, and I will of course that clarify it. Even in live session also uh, you can raise your problem if you are understanding any problem in this course. And if you have any query, then you can directly ask me, and also you can ask also later on by email also. If you are not comfortable here, you can clarify it later on also. So we have given that different issues on that chemical process intensification. Some fundamentals in the beginning we have described, even some of the different actually categories of the chemical process intensification that we have described in the courses. Uh, we have given that the that basic definition of the process intensification, and that process intensification based on what that based on that different criteria, maybe that size of the equipment, economy, environmental issue, all those things. And we have discussed several processes of chemical engineering where that process intensification of those chemical process can be done, and also can be developed in other way based on the different idea and the fundamental theory. So in that case, we have described that some process intensification may be based on that, reducing the size based on that. Sometimes the some if it is a multi-phase flow, they are interfacial area of the phases, because most of the chemical engineering processes that depends on various factors, whether it is single phase flow or multi-phase flow, and all those multi-phase flow, whether it is in a streamline or laminar flow, turbulent flow, and if it is laminar flow, how that gas liquid or gas liquid solid flow, that is multi-phase flows are flowing in a particular reactor or in a conduit, so that they are forming some basic flow pattern, and then how that flow pattern can be changed to get that more yield of the process, those things also. Even how that interfacial area play an important role in that process intensification of the chemical processes. Even how to develop that interfacial area that we have described also in downflow system, that where that if suppose the liquid extraction process or gas liquid operations there, where you need to disperse some non you can say that that is immiscible fluid in another continuous liquid, where that immiscible liquid will form in a dispersed phase of bubble or droplet. So there, to get the more interfacial area, you have to increase the size of the droplet or bubbles. and also you can produce more retention time to get that more absorption or adsorption or extraction process there by producing more finer bubbles, and also that moving or allowing that droplet or bubbles against the buoyancy, so they are to get that more retention time. So in that way it is also the intensify the process. Another important process that you can intensify the process by cavitation, that we have described earlier also. Various cavitation process you can use to intensify the process. One of the important process intensification in extraction is that supercritical extraction for the process intensification. So in that case, you know that intensification of the separation technologies with fluids at high pressures, which are essentially vital to get new natural products. And among the intensified extraction techniques, the supercritical fluid technology offers like products free of residual solvent, and that typically present high quality when that compared to the products that obtained by conventional techniques there. So this is a very important for intensification of the process at high pressure. Now the extract of that bioactive compounds, as an example, can be obtained by extraction of solid matrix like leaves, seeds, pulps, etc., or by extraction or fractionation of liquid mixtures in aqueous solutions like fish oils, microalgae oils, vegetable oils, deodorized distillates, etc. And in that case, at high pressures, you will see that we are near or above the critical point, pressure and temperature. Uh, the solvent density increases drastically, and this is the most important parameter associated to the solvent for extraction. Now, what is that actually then supercritical extraction? This is basically a separation process. This is one component is separated as an extractant from another as a matrix by using supercritical fluids as the extracting agents. It is basically a diffuse based process uh, in which the solvent is required to diffuse into the matrix, and the extracted material to diffuse out of the matrix into the solvent. Now, diffusivities in that case are much faster in supercritical fluids than in liquids, and therefore this extraction can occur faster. And this is the main mechanism of this process intensification by these supercritical fluids. Now, in that case, carbon dioxide is non-toxic substance which acts as a solvent. Even it is used as a co-solvent or anti-solvent. It is the most important fluid which is used in fluid technology, especially for the extraction process. Even some other separation processes it is being used. Sometimes microionization process and encapsulation process also it is being used. So it is applied to obtain extracts concentrated with bioactive compounds for like food, pharmaceutical, and cosmetic applications. Now in this case, this non-toxic substances in that case has a critical temperature, like in this case carbon dioxide, near to room temperature, that contributing to the operating conditions. especially for pressure and temperature, to extract some, thermolabile substances such as bioactive compounds. And you can say it is non-polar, and to enlarge the application spectrum to extract these bioactive compounds like ethanol, water, or both are usually used as co-solvents there. Now, if this carbon dioxide acts as co-solvent, when the mixer it is used more than 60% of ethanol or water, and as anti-solvent when the solute extract is not soluble in carbon dioxide during the depressurizing step. So in that case it will be used as co-solvent in the mixer. Now it is one of the important aspects to know that whenever we are talking about that supercritical fluid like carbon dioxide or ethanol or water, in that case what are the phase diagram for that, thermodynamic phase equilibrium conditions, what are those that you have to know. I have given those figure in module, I think it is in lecture number 13 and module I think 12, 30 module 12 there, and I think there I have described that what are the different phase equilibrium points or limits for the mass transfer among different phases there. And in that case the triple point of carbon dioxide is at pressure of 5.18 bar and temperature of 216.58 Kelvin. It is around minus 56.57 degrees Celsius. And the critical point is at pressure of 73.7 bar and a temperature of I think 304.15 Kelvin, which is around 31.1 degrees Celsius. And when the substance is in the state above the critical temperature and the critical pressure, it is called supercritical fluid. So in that case, the figures whatever I have given, they are that phase diagram of PT for carbon dioxide and the substances most that commonly used as co-solvent like ethanol, water in high pressure extraction processes of bioactive compounds are given there in the figure. Now you have to know parallel that what should be the solvating power of a solvent. Now in that case you know that density is the most important thermodynamic property to define that solvating power of a solvent at high pressures, which increases the density of the solvent. If you are increasing that, then you will increase that its solvating power. Now you will see that for carbon dioxide the critical point is at the pressure of 73.7 bar and the temperature of 304.15 Kelvin. It makes that carbon dioxide the most applied solvent to extract thermosensible substances there. Now whenever you are going to do that supercritical fluid extraction for the process intensification, what should be the general process step? Generally the supercritical fluid extraction that applied to a natural solid matrix that consists of three steps: the system, supply of solvent or co-solvent, the extraction unit, and the extract separation system from solvent or co-solvent. Okay. Hello, yeah, Shagar Mahajan is there. Hello, yeah, good afternoon. Yeah, if you have any queries, please ask any. Then I can clarify it. If you have any doubt in any contents there in the slide. So I have given the general scheme of the supercritical fluid extraction unit. There you will see that there will be some one unit, that extractor, then carbon dioxide plus extract, then it will go to the separator, and then it will be sent to through this condenser, then extractor would be separated, and then carbon dioxide again to be that liquefied, and then liquid carbon dioxide will be sent back to after compressing to that that extractor, like this. That schematic diagram is given. Now in that case, the supercritical solvent continuously flows through a fixed bed of solid particles and dissolve the extractable components of the solid. Now solvent is fed into the extractor and evenly distributed at the inlet of the fixed bed. The system solvent and soluble component leaves the extractor and feed the precipitator or separator, where the solvent products are separated by expansion there, that is depressurizing. And you know that since at low pressure the density of the solvent sharply decreases, therefore it decreases the solubilizing power of the solvent as well, and the products are precipitated there. Now you have to you have to choose operating condition for that particular supercritical extraction process. In that case, now the choice of the operating condition, generally pressure and temperature, of course are the determining factors that contributes to the maximizing of the extracts solubility in the supercritical solvent, and consequent to the extraction yields. The increasing the density of the supercritical fluid, you will see that the solubility of the solvent will maximize, and the solubility increasing can also occur when a co-solvent is added there, and this will change the solvent power, and then this way you can say that new solvent is a mixer will be there. Now to design that high pressure fluid extraction process of valuable compounds from that new natural solid matrix, it is necessary to know that to define the size of the extraction unit and some important parameters that have to be determined to obtain the optimum process conditions for its application. And the most important parameters that you have to remember, that among the variables that determine the process are that operating conditions, that is pressure and temperature, amount of solvent, how much amount to be given, conditions of solvent removed from extract, that is precipitation, pre-treatment of solid matrix, and other mass transfer parameters. And the mass transfer at processes at high pressures, that is basically related to the configuration of the bed, the particle size, the height, and diameter, preparation of raw material, the solvent flow, like this. And some properties of that carbon dioxide that is to be take into account, like carbon dioxide properties there. What will be the viscosity, what should be the diffusivity, what should be the thermal conductivity, what should be the dielectric constant, that everything should be known to you at a particular temperature and pressure there. Now if we talk about that, where then this supercritical extraction to be applied there, basically essential oil extraction is mostly used like isolating that essential oils, the use of carbon dioxide as supercritical fluid, that has been considered as a chemically green, unconventional extraction technique that does not alter or degrade the substances that present in oils, because it that uses relatively low temperature in the extraction process. Another example like that, that phyto, sterols are non-volatile, triterpenes there. In that case, the great majority uh, of these compounds are formed by carbon with one or two carbon-carbon bond, that is double bonds there. So these compounds have various biological activities, such as lowering the total serum or plasma cholesterol levels, and the low density lipoprotein cholesterol levels, like this. Uh, in addition, you can say that they have that anti-tumor activities also, which inhibiting the development of that colon cancer. Now, for the extraction of these phytosterols, the supercritical carbon dioxide has been shown to be an efficient technique for extraction of fixed oils from vegetable matrix. You will see that this supercritical extraction sometimes used for carotenoid extraction. This is basically carotenoids are basically terpenes that present in plants, that have several applications in food, cosmetic, and pharmaceutical areas. Now, this supercritical extraction will give you the intensification of this process, for extracting the compounds, that using low temperature, and which is very beneficial in a short time in relation to conventional processes, and does not use toxic solvents there. This toxic solvents, it is not there to collect that compound of that interest. So that is why this carotenoid extraction is being done by this supercritical fluid technology. Other application like fatty acid extraction, you will see that these fatty acids that belong to the lipid class and differ according to the size of the carbon chain. Basically 2 to 80 carbon is there, and the presence or absence of these double bonds, that means saturated or unsaturated condition, or their that radical function as the groups, that hydroxy, epoxy, that, or hydrogen atoms there. So this type of fatty acids generally is extracted based on this fluid supercritical technology. Now, some of its applications are in food, uh, nutraceutical, and cosmetic, industries, and in the production of lubricants, biodiesel, and the glycerol. Now, extraction of those fatty acids by these supercritical fluids, that means at high pressure, carbon dioxide is actually giving the better yield, even better performance compared to the other method. You'll see that sometimes this supercritical carbon dioxide, that based extraction, there will be sometimes that supercritical carbon dioxide modified with the ethanol and water system. Now, in that case, this extraction with supercritical carbon dioxide is modified with water in different proportions, and which is carried out to obtain that bioactive compounds of high polarity, because in this case carbon dioxide is a non-polar molecule, and it does not have power to solubilize it polar substances, as is the case of that phenolic compounds which has happened there, like phenolic acids and flavonoids. And you will see in this case this solvent flow rate, percentage of co-solvent type like ethanol or water, even extraction time, those actually directly implicate the yield of these substances at the end of the extraction process at high pressure. Now, you will see there are other subcategory of the supercritical, like that supercritical versus subcritical extraction. In that case, you will see that supercritical being a much stronger solvent than subcritical carbon dioxide, which allows for faster and more complete extractions. For supercritical method, the lighter oils as well as that not so desirable higher molecular weight materials like waxes, paraffins, lipids, and resins that can be extracted. And these fatty waxes will then need to be removed from the extract by a process that is called, winterization. So, at this supercritical condition, whenever you will see that the process will be run, that in that case these fatty waxes need to be removed from that extract by that other process. Now the advantage of that subcritical over supercritical is that the extracted oil is pure, free of fats, waxes, and lipids. So less post-processing work, if any, is required there. And the pure oil does not need to be further refined and can be reused just as it is edibles and other products. Now I told that there will be some winterization process. Now based on this method, the extract is mixed oil with alcohol and then put in a deep freezer overnight. The next day, the mixture is poured into a funnel through a filter paper, trapping the waxes and lipids. And this process can be done several times to completely filter all the unwanted elements there. So once the oil is filtered, you'll see that the alcohol is removed by heating the oil extract using a rotary evaporator. Now, main question is coming that why that carbon dioxide extraction it will be safer, purer, and cleaner. There are a number of advantages of this extracting with carbon dioxide, whether subcritically or supercritically. Now, one is that to trace that is, there will be no traces of that solvent left behind, versus other methods of extraction using this type of hydrocarbons there. Carbon dioxide is not a volatile solvent there, so there is no need for special safety equipment here in this case. And also we can say that carbon dioxide is relatively cheap and can be recovered and recycled. Around 90% of the carbon dioxide that is used in its extraction process. And also some other strategies for this carbon dioxide based extraction process at this supercritical condition. Some general strategies are as follows for that optimization of the process. Like you can say that maximizing the diffusion. This can be achieved by that is increasing the temperature, swelling the matrix, or reducing the particle size. Now, matrix swelling can sometimes be increased by increasing the pressure of the solvent and by adding modifiers to the solvent. Now, some polymers and elastomers in particular, you will see that are swelled dramatically by carbon dioxide, with diffusion being increased by several orders of that magnitude in some cases. And to maximize that solubility, generally higher pressure will be increased. Higher pressure will that means will increase that solubility, and that the effect of temperature is less as close to the critical point. And increase in the temperature that causes a decrease in density and hence dissolving the power. At pressures well above the critical pressure, solubility is likely to increase with temperature. Now, adding to low levels of modifiers such as methanol and ethanol can also significantly increase solubility, particularly more polar compounds there. Now, to optimize that flow rate, what you have to that the rate of extraction, the flow rate should be high enough for the extraction to be completely diffusion limited, but wasteful of solvent. Now, in that case, you need to minimize that solvent, minimize the amount of solvent that is used. Now, to minimize that amount of solvent used, the extraction should be completely solubility limited. But in that case, you have to be very careful that whether it should be very long residence time or not. Now, flow rate must be therefore determined depending on the some competing factors like time, solvent cost, capital cost of pumps, heaters and heat exchangers. So that there are several issues on that, then carbon dioxide extraction, how it can be done. So we have analyzed different issues of this supercritical extraction based process intensification. Okay. So if you have any doubt or any query that you can ask, so that we can discuss more about that. Another issue in process intensification, that like microprocess technology, that process intensification. You know that chemical synthesis and processing by application of a continuous flow microfluidics. Now it is very important for intensification of the process there. So in that case, we have to know basic about that chemical microprocess technology. In that case, you know that flow microfluidics is very important devices, or you can say that it is basically a science. Microfluidics is a science actually by when the fluid flow in the range of microliters to picoliters in networks of channels with dimensions from tens to 100 micrometers there. So in that case, these microfluidics are nowadays attracted to the researchers, even scientists in different research organization, the how to get that process intensification by this channel based system, where we can get more yield for that particular reaction system or any physical operations also, just by just by controlling that plug flow phenomena there. You know that in conventional processes you will see that in several issues where you will see that back mixing is one of the shortcomings of that process, which reduces the yield sometimes. So there, so to get that minimized that back mixing process and also intensify the process yield there, or to get the more performance of the process, now it is that micro fluidics, that means micro channel based systems are gaining importance as inexpensive means of achieving such processing there. Now, basically that you have to know that some definition of that, that reactors which is used for these objectives are generally smaller and can be called as the chip based reactors, or you can say it will be a micro reactors. And the reactors that having a microstructure zone can be better named as microstructured reactors are there. This is basically channel based reactor. In the channel that gas liquid reaction or liquid liquid extraction process, or you will see that some other physical operations like that heat exchanger, they are channel based heat exchanger, they are because of that plug flow phenomena, that means reducing that back mixing there. Now the execution of that chemical process inside a small volume, typically inside channel with the diameters of less than 1 millimeter, that is called micro channel based reactor, or other structures which have that sub millimeter dimensions in that geometry. And chip based reactor is dealt with the operation of a large number of that parallelized micro channels there. Now microreactor and microreactor and chemical microprocessing, are there any difference? Of course there. In this case you will see that microreactor basically technology driven definition, that is older definition is like a micro reaction. Accordingly it is termed as device that is at least made by the micro fabrication or modern precision engineering techniques. As a result, in that case, microreactors have some sub-millimeter internal dimensions. Now, application-driven definition, they are mostly the present definition. You can say that for this process intensification system, a microreactor is actually casing for performing reactions that is designed based on flow patterns with the characteristic dimensions that is much below that of conventional apparatus, typically below the sub-millimeter range. And you will see that chemical microprocessing, in that case it will be basically the synonymous with simply using that microreactor for an application. That is replacing conventional equipment by novel microreactors. So in that case, chemical microprocessing, it is based on process design in a unit cell before manufacturing new or selecting existing microprocessing equipment. In that case, that it is composed of a multitude of such cells, and this results in having tailored processing equipment at the microflow scale there. Now question is that what are the basis for this process intensification in that microreactor? Now, a microreactors, especially those having large throughput, may fulfill the criteria of the process intensification. Chemical microprocessing can be regarded as a branch of process intensification. More often, process intensification will rely on novel, especially designated reaction that will be equipped in such way that should be scale up in nature. That means at large scale that will be designed. Now, process intensification, that device, whatever developed, usually cannot refer to a unit flow description of giving that microreactors, because in that case they are dealing with non-micro flows there. And in that case, you know that to develop that microreactors, channel-based microreactors for this microfluidic flow, and that you have to, design that flow internally in such a way that some, favorable feature of many microflows to be, designed in such way there will be such regularity or symmetry where you will see that in a certain fashion that internal flow inside the reactor will happen. So that is why we'll suppose if we design some microreactor, then you have to manifold repetition of internal flow structure as a constituting element there. So this relates to flows in channels with channel arrays which will be parallel to each other. Now this flow symmetry concerns the flow within one microchannel that may be radial extension like circulating flow, the axial evaluation like slug microflow like this there. And microflow processing, in that case the repetition of the unit cells not only holds at the laboratory scale but may also be applied to a smaller or larger production as well. And this can be achieved by numbering of the elements, that is by multiple repetitions of the small precisely structured regions there inside the reactor. Sometimes that numbering up will be done internally or externally. So external numbering up, generally the connection of many devices in a parallel fashion, whereas internal numbering up, it means that the parallel connection of the functional elements only rather than of the complete devices. Now these elements are, you'll see that grouped in a new way, usually as a stack, and are encompassed in a new housing there. So I have given that description in the slides, go through that, and some features of that chemical processing which favor the choice of either external or internal numbering up. Like sometimes for external numbering up, in that case favors low degree of parallelism, favoring multi-phase processing including powder making, bubble or droplet or film formation movement, surface flows, especially complex processes, precious products, functional chemicals, slow reactions process, that is demand for laminar flow, processing, etc. by delay loop. Even hazardous processes also there. Whereas internal numbering up will give you the favor of high degree parallelism, favoring single phase processing, stream guidance, volume flows, unit operations, standard reactions, bulk chemicals, fine chemicals, fast reaction or process. In that case, no demand for the laminar flow. Also, you'll see that post-processing processes, process completed within the device, and it also will favor the safe processes there. And you will see that some microreactor will be microchip based reactor for the flow chemistry there. In that case, for a very small amount of liquid will be used in a particular cell of that channel cavity there, that you have to do that reaction in a particular temperature and process, and you will see that within a certain low retention time you will see that the process will be higher. I have given some example of that microchip based reactor for flow chemistry there in the lecture also, and some commercially also available flow chemistry there. So it receives increasing interest in the field of both microtechnology and chemical engineering to the scientific and academic communities. Chemical processing and even new chemistry in microchannels that enable laboratory scale studies of large depth, large flexibility, and notable fastness in gaining information there. Some advantages like the length scale of the diffusion process is compatible, and also it will be comparable to that of microchannels or even in that shorter channel. Efficient mixing of reactants that can be achieved during very short times, typically milliseconds. Enhanced heat transfer due to the larger surface area to volume ratio, and enhanced mass transfer. The good heat transfer properties allow a precise temperature control of reactions. Now for that you will see that uh, consequently the connected thin fluid layers which will give you the heat transfer and often also mass transfer are very rapid way. And you'll see sometimes that continuous production using that microreactor technology that will meet the throughput requirements by either scaling out, or you can say that by numbering up. Scaling out basically for stacking large microreactors, whereas numbering up, that will be microreactor parallelization. And the desired total productivity that can be obtained also simply by a linear increase of the productivity of individual microreactors that can be uh, circumventing that conventional scaling up problems. It is also possible to change that temperature of microstructure reactors very rapidly to intentionally achieve a non-isothermal behavior there. Now you will see that for that a small channel based microreactor or millichannel, or you can say microchannel based microreactor, you will see that small hold up that reduces the damage potential of the explosions or other hazardous state of mal-operation there. So it is advantageous in that direction. Also you will see that some selectivity will be increased by suppressing side reactions and by additional effect of precise setting of residence time. The content of follow-up reactions that can be reduced. You'll see that in many reaction processes that the operation at the kinetic limit that may not superimposed by the transport phenomena. So in that case, it will allow one to reach that high space-time yields, so that compact reactors and plants that will result. And other advantage like the small dimensions can prevent explosions intrinsically. Uh, Basically, when the large channel interfaces that favor radical termination over radical generation and growth. The symmetry based reactor design channel to plate to stack to multitude of stacks, and the flexibility in operation provide a high degree of modularity to adjust the production rate and the bridging to process system engineering. So in that case it will be advantageous. Now, what is the direction then in chemical process intensification? Now, the aim of microprocess engineering is not primarily to miniaturize the production plants, but to increase yields and selectivities of chemical reactions, thus reducing the cost of chemical production there. So, you have to design that microreactor in such a way that sometimes that reducing that plant size that may not give you that higher capacity production there, but in that case to if you are numbering up that systems with that proper channel based micro reactors, then you can get more productivity based on that intensified yield. So this can be achieved by either using chemical reactions that cannot be conducted in large volumina, or by running chemical reactions at parameters like temperature, pressure, concentrations, and that are uh, uh, you can say that accessible in larger volumina due to the safety constraints. And the small geometric dimensions that result in an intensified mass and heat transfer, which often leads to the increased yield and selectivity compared to the classical batch approach. Now, various dynamic features with the physico-chemical requirements of the reaction, like relation of you know reaction rate with mixing rate, relation in mechanism with flow pattern, relation of reaction time with the residence time, relation of exothermally that is operated reactions with the heat transfer there. So these various dynamic features with the physico-chemical requirements of the reaction to be you know uh, interrelated. So dimensions of the process intensification in microreactors, basically several categories are there, like increased yields and selectivities. In that case, increased yields and selectivities are directly tangible to green improvements in chemistry when using microprocess technology for process intensification. Now, increased reaction rates, in that case, step change increases in reaction rates, which come from increases in temperature, pressure, or concentration, and it can be achieved in the some specific manner, like fast simultaneous carrying out of process steps such as multiple reactant dosing, function integration, that means combined reaction and separation, reducing downstream expenditure, and also you can say that energy efforts through better upstream performance. Now, accessibility of the exothermic and thermal runaway reactions, in that case fast and exothermic reactions which leads to the formation of undesired products can be controlled in microreactor by hotspot assessment. Also, you can say that microreactors that allow a reduction of the risk potential when dealing with toxic or explosive reagents, which make formerly scalable reactions that is accessible to further development. And increased efficiency in terms of low volume operations, uh, online reduction, monitoring, elimination of scale up or multiple transformation. In that case, you will see that increased efficiency will be less input and waste. So a major proportion of that waste in a chemical reaction is the solvent, which typically constitutes 90% or more of that overall mixture there. Now, in that case, microreactors, allow want to reduce the content of the solvent by increasing the concentration of reactants. Now, what should be the different aspects of that implementation of process intensification? Now, in that case, you have to remember that for increasing mass transfer for gas liquid reaction, these are the aspects. Even you will see improved mass transfer via the larger gas liquid interface, changing the reaction mechanism through solubility effects like supercritical state, using steric effects, volume of transition state. You will see that to guide the product and isomer selectivity, process intensification by pressurized high temperature operation, changing the product type using high pressure and temperature, the influence of pressure on speeding up chemical reactions, increase in rate constants by changing in activation energy and free exponential factor. So these are the some aspects of that implementation of that process intensification based on this microreactor technology. So we have described several issues on that in this courses. You can go through even other reference books to get more details on that. I have given some references for further reading there. So you please go through that. And if you have any further queries, you can write to me and I can clarify it. And if you have any other doubt, anytime you can drop a mail to me. I'll try to give you clarification for that. So thank you for being live in this live session for this, and I wish all the best for your exam ahead for this course. Thank you.